So today we're going to be talking about this idea of a normal distribution and this phrase known as the empirical rule. And what does the empirical rule really mean? So yesterday, or the last time we met, if you're following along with me, we talked about percentile and standard deviation. We used some of these dot plots similar to the one below to be able to find the percentile. And then you talked about how we can find the standard deviation by hand, but we also looked at how technology can help us find standard deviation. So for today, we're going to be taking that idea of standard deviation and we're going to be implying or putting it in with what is known as the empirical rule for a normal distribution. To start, to understand what a normal distribution is, we have to start with this idea of what is known as a density curve. So if you're following along with my notes, you can go ahead and pause and fill this out really quickly. All right. So here we see that it says that the description, that a density curve is the description of the overall pattern of the distribution. So sometimes this one looks pretty normal, and we're going to talk about what that means, but is this kind of line over my actual distribution of data? So if we look at it in this example, this was just a diagram talking about glucose levels, and this is talking about what percent falls into each of these bins. So this is actually a histogram here, and then the density curve is laid on top of that. And we can see that we're talking about the percent. Each of these, like this one, says slightly more than 15% falls exactly in this bin, which might be like 98 to 110. We don't have those exact numbers here, but this line right here is what is known as my density curve. It shows the overall pattern of my data and how that data falls. So some things about density curves, this area beneath your density curve is always going to be exactly 1. No matter what the shape is, the area is going to be exactly 1. And because the area beneath it, that's this part here, represents the percent or the proportion of the data that falls in a specific chunk. So my example said, what if I want to know the percent of glucose levels under 100? If I come up here, I can see that this is my 100. So I could draw that up to my density curve. And what I'd be finding is this area. If I had the ability to find this area, that would tell me the percent of glucose levels that fall under a 100. Well, we know that all of our percents added together have to equal 100. And so that's why it has exactly an area of 1 beneath it, because if you took the area of the entire thing, well, you would have your entire population or your entire sample, all of your data. And so you would have exactly 1, which is pretty cool. So there are many, many different types of density curves. We can have ones that are skewed. Sometimes you'll see ones that look like this. So notice here, there's this really long tail, and then you have your little bump there. Sometimes you might have ones that are known as bimodal, and so they have 2 peaks. So all of these are still density curves, and they'd still be explaining this data. So you would still have little histograms that went with it. This is just a brief little drawing here. So your data might look something like that, and the density curve approximates that data. All of this stuff would still be true. The area beneath the curve in between any 2 parts would be the percent of the data that falls within those 2 parts. And then also, the area beneath it would be exactly 1 because it represents the area of the entire thing represents all of your data. So for our class, as a very introductory class, we want to know just about what are known as normal curves. So let's talk about some things that are normal. Normal distributions are pretty because they have a few things. So normal distributions, as you can see both here and here, these are both normal distributions. They're always going to be symmetrical. They're always going to be single peaked, so not like that bimodal one. There's always just going to be a single peak, a single mountaintop, and it has this really cool bell shape to it. So if you've ever heard of a bell curve, we're talking about a normal distribution. So this kind of looks a little bit like a bell. If you were to draw a little thing there, you could have your little, this is your bell. That would be your thing that swings back and forth. All right, so when we talk about a normal distribution, normal distributions have the data distributed in a really, really symmetrical way. And it has to be, it's based on both the mean of the data and the standard deviation of the data. And so that is how we represent it. We talk about it being the mean and the standard deviation. So notice here, if you see something like this, the n says it's a normal curve. The mu, we now know, stands for the mean, and sigma stands for the standard deviation. So if I gave you something as n 17, 2.6, then we know that the mean is 17 and the standard deviation is 2.6. So just a very, very basic example of that. So for a normal curve, what is always, always, always going to happen is that the mean is always going to be at the center of the normal curve. So if we zoom in, here we're using x, but x with a bar is the same thing as mu. That just means the mean. And notice that it is right here at the center. So that is where you're always going to find your mean, is smack dab in the center. These kind of cutoffs then are based on the standard deviation. So here it says that one standard deviation is noted as the distance from the center to the change of curvature points on either side. So it's kind of weird wording here, but I'm really going to zoom in and show you what that means. So let's really look in at this. So here I have my mean. This would be my first change of curvature point. And notice here it's saying that to go from here to here, that would just be one standard deviation away from my data. And this would be in the negative direction. This would be in the positive direction. So if we even look at that very basic example I gave you, if this was 17, then this would be one standard deviation beneath that. So 17 minus 2.6, which is going to give me 14.4. 17 plus 2.6 is going to give me 19.6. So this is where my mean would be, and then this would be my standard deviation, and then you could keep going. So that was within one. This one is going to be within two standard deviations, and then the next curvature would be three standard deviations away. So I can even do, we keep doing the three, let's go in the positive direction. 17 plus 2.6 plus 2.6 plus 2.6. This would be a 24.8. So I've added my standard deviation 3 times in order to get here. And remember, this is really over a histogram. So this would really be, if your data was here, what that would look like. And so normal curves are really, really cool because specific amounts of your data is always going to fall within these categories. We love it when our data is normal because they fall within these categories, which is really cool. One of the last things here is that for a normal distribution, the mean always equals the median, which is not the case with a lot of data. As a teacher, I look at your guys's data on assessments a lot, and often, honestly, the median is higher than the mean. And that's because there's our means or medians are typically in like the 80s. There's only 20 points between an 80 and a 100. So there's only 20 possible points to get there versus the other 80 between a 0 and an 80 that people have the option. So we have what's known as a trail beneath the data. So other data, they don't always line up perfectly, but if it's normal, then your median and your mean really are going to line up perfectly, which is cool. So we like normal data. Normal data is really cool to see. And here are just some examples of things that you actually interact with that are typically normalized. So one of them is test scores on the standardized tests, so like the ACT, the SAT, your AP test. A lot of those are going to follow this pattern. So the majority of people are going to fall within this category of this is the average, and then within one standard deviation on either side. Very few people score 3 standard deviations away the mean. If you are, you're definitely in that high 5 category for an AP exam. These are the people getting the 36 on the ACT. Versus on the other side, thinking about an AP exam, if you're in this small category here, you're the people getting a 1. These might be around the 2s. You know, the 3s are probably in here, the 4s, the 5s. It's not always going to be perfectly that way, but it's going to approximate that. So test scores are very, very often normal. Other things that we see that are normalized typically are characteristics of biological populations. And so if we're talking about traits, so like height, weight, things like that, we can often normalize what those would look like. And then last but not least here is repeated measures. And so what we mean by that is that if you repeat a study multiple times, your data is typically going to normalize. It's going to end up falling in this category. If you do the data over and over and over using different samples and things like that, then more often than not, you're going to see it fall into this category of normal one. So we're going to pause right here if you're following along with me, and you're going to go do your first check-in, and then we're going to come back and we're going to actually do some practice with just finding this kind of stuff, your bins, your standard deviation cutoffs, and then what percent of data actually falls here.